Hi everyone, my name is Dr. Raghava. I am working as Professor and Head of the Department of Civil Engineering in LIET Institute of Engineering and Technology. So today I would like to discuss topic of fluid mechanics, that is applications of Bernoullis equations. What is Bernoullis equation? We know that Bernoullis equation is nothing but P by W plus V square by 2G plus Z is equal to constant. So this is known as Bernoullis equation. P by W is known as pressure head. V square by 2G is known as velocity head or kinetic head. Z is known as datum head. P by W plus Z, that is the sum of pressure head plus datum head, is known as piezometric head. So Bernoullis equation means sum of three heads, that is total energy, is constant. Bernoullis equation for ideal fluids. When we are considering two different sections, P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. So that is Bernoullis equation for ideal fluids. And P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2 plus HF, where HF is known as head loss due to friction. This is Bernoullis equation for real fluids. And already P by W, you know, pressure head, V square by 2G is velocity head, P by W plus Z is known as piezometric head. So Bernoullis equation is applied in all problems related to incompressible fluid flow where we are considering energy. And these are the following applications of Bernoullis equation. So number 1, Venturi meter, number 2, orifice meter, and number 3, petard tube. So out of Venturi meter and orifice meter, they use it to measure discharge only. Petard tube is the only instrument in fluid mechanics with which we can measure velocity directly in the laboratory. So now let us see the function of Venturi meter and parts of the Venturi meter. Normally Venturi meter consists of three parts. Number 1, convergent cone. Number 2, cylindrical throat. Number 3, gradually divergent cone. So I will explain parts of Venturi meter. So this is our Venturi meter. It is known as convergent portion. So the cross-sectional area is decreasing gradually here. Here you can see a cylindrical throat. Cylindrical throat. After that, gradually divergent section. Normally, length of gradually divergent portion is greater than length of convergent portion. And here see the angle. The angle of convergent cone normally 20 plus or minus 1 degree, around 19 or 21, like that we can consider. And here the angle at outlet is equal to 5 to 15 degrees centigrade. Normally we are providing 6 degrees. Right. Suppose if you observe this figure, Venturi meter, it is upstream side of the Venturi meter where the flow starts. So here diameter is equal to capital D, and after that you can see convergent cone here, and throat diameter is equal to small d, and this is divergent portion. Length of divergent portion is greater than length of convergent portion, and here this side is known as downstream side. So now what we are doing, by reducing the area, pressure difference between these two sections is created. So that pressure difference can be measured using manometer, differential manometer or single column manometer, whatever may be the type of the manometer, we can easily measure. So same thing, length of convergent portion, already 2.7 into capital D minus small d, where capital D is equal to diameter of the pipe, small d is equal to diameter of the throat, and length of the throat. Again there is a relation between length of the throat and diameter of the throat also. Similarly, pipe diameter and throat diameter is also, it is there. Normally throat diameter should be 1/3 to 3/4 capital D, diameter of the pipe. Normally we are considering small d is equal to 0.5 into d. So half of the pipe diameter, normally throat diameter we are considering. To avoid separation of fluid flow, normally large length is provided for divergent portion. Differential manometers or mechanical gauges are used to measure pressure difference between these points. And not only that, this venturimeter is mainly depending upon principle of Bernoullis equation. This already I have told you. And in this case, no projections will be there, no sharp corners, no sudden changes in contour are occurring in case of venturimeter. Next, whenever cross-sectional area is decreasing, then what happens? Pressure is decreasing, velocity is increasing. So pressure head is decreasing, velocity is increasing. At throat, what is happening? Pressure also remains constant, cross-sectional area also remains constant, velocity also remains constant. Coming to divergent portion, as cross-sectional area is suddenly increasing, then what happens? Velocity is decreasing and pressure head is increasing. So in this way, we are balancing velocity head and pressure head at different sections. So as the fluid enters into the divergent section, the pressure is largely recovered and lowering to velocity of the fluid. At divergent portion, what is happening? Velocity is decreasing and pressure head is increasing. So what is the major disadvantage of this particular equipment? So maintenance cost is very high, installation is also very high, and installation is very, very difficult. Inspection also very, very difficult since it is a small instrument. Next, the Venturi effect. It is mainly, we are considering a particular pipe. And where the velocity is increasing, where kinetic head is increasing, where pressure head is decreasing. So all these things we have to study. It is mainly depending upon Bernoullis equation as well as continuity equation also. Continuity equation is nothing but discharge is constant. Q at two different sections, A1 V1 is equal to A2 V2. So similarly, the equation of venturimeter is obtained from Bernoullis equation as well as continuity equation, and it is also depending upon incompressible fluid flow. Now expression for determination of discharge. D1 is equal to diameter at section 11. P1 is equal to pressure intensity at section 11. V1 is equal to velocity of flow at section 11. Now we know that cross-sectional area at section 11 is equal to pi by 4 into diameter 1 whole square at section 11. Next, similarly, D2 and P2, V2 and A2 are diameter, pressure intensity, velocity and cross-sectional areas at section 2. Now we know that Bernoullis equation at two different sections. P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. So since the venturimeter is horizontal, pipe is horizontal, Z1 is equal to Z2. We can cancel on both sides. So P1 by W plus V1 square by 2G is equal to P2 by W plus V2 square by 2G, where W is equal to rho into G also. So P1 minus P2 by rho G or P1 minus P2 by W is equal to V2 square by 2G minus V1 square by 2G. But P1 minus P2 by W is the difference between pressure heads at sections 1 and 2. It is nothing but small h. Small h is equal to P1 minus P2 by W. So substituting the value of P1 minus P2 by W in the above equation, we will get h is equal to V2 square by 2G minus V1 square by 2G. That is kinetic head difference between section 2 and section 1. Now what we are doing, we have to apply continuity equation at sections 1 and 2. So continuity equation is nothing but discharge at two different sections is constant. A1 V1 is equal to A2 into V2. So now V1 is equal to A2 into V2 divided by A1. So now substituting the value of V1 in the above equation, h is equal to V2 square by 2G minus V1. In place of V1, what I am doing? A2 into V2 divided by A1 whole square divided by 2G. By taking common, V2 square by 2G common, V2 square by 2G bracket begin 1 minus A2 square divided by A1 square. So this can also be written as V2 square by 2G into A1 square minus A2 square divided by A1 square. So V2 square is equal to 2GH into A1 square divided by A1 square minus A2 square. Now we want to calculate V2 only, velocity at section 2. V2 is equal to square root of 2GH into A1 square divided by A1 square minus A2 square. So if you consider square root, then you will get A1 by square root of A1 square minus A2 square into square root of 2GH. Q is equal to A2 into V2. So now we have already calculated the value of V2. So now I am substituting the value of V2 in this equation. Q is equal to A2 into V2. V2 is nothing but A1 divided by square root of A1 square minus A2 square into square root of 2GH. So now this can be written as A1 A2 root 2GH by square root of A1 square minus A2 square. So this above equation gives discharge under ideal conditions. So this discharge is known as theoretical discharge. So actual discharge will be normally less than the theoretical discharge. Theoretical discharge means using some formula we are calculating the discharge, that is known as theoretical discharge. So actual discharge means by collecting in a measuring tank we have to calculate the discharge, that is known as actual discharge. So actual discharge is represented with letter Q actual. So Q actual is equal to CD into A1 A2 root 2GH divided by square root of A1 square minus A2 square, where CD is equal to coefficient of discharge for Venturi meter. So CD is defined as the ratio of actual discharge to theoretical discharge. Normally CD value is always less than 1 because actual discharge is always less than theoretical discharge. Its value is ranging from 0.97 to 0.99, coefficient of discharge value. Normally we are considering as 0.98 for Venturi meter. Next instrument is orifice meter or orifice plate. It is also a device which is used to measure rate of flow, that is discharge. It is a cheaper device when compared to Venturi meter. It is also working on the principle of Venturi meter is nothing but Bernoullis equation only. It consists of a flat circular plate which has a sharp circular edge or hole which is known as orifice. Next, the orifice diameter is generally kept 0.5 times diameter of the pipe. Normally it is varying between 0.4 to 0.8, but normally we are providing 0.5 times. And a differential manometer is connected at two different sections to measure the pressure difference between these points. So if you see, this is an orifice plate or orifice meter. It has sharp edges. It is a pipeline. It is a plate which is having hole. It is fixed in this particular pipe. So this is known as orifice meter. So in this case, in coming to Venturi meter, there is convergent portion and throughout there is gradually divergent portion. So this type of arrangement is not available in orifice meter. So if you see this figure, here direction of flow is there. Here before plate, what is happening? Cross-sectional area is decreasing, area of flow is decreasing, and here it is reaching, and after that vena contracta is formed. Vena contracta where less cross-sectional area is there. After that vena contracta again area is increasing. So now we are considering two different sections, 1-1 and 2-2, 1-1 and 2-2, and a differential manometer is connected to measure the pressure difference between these two sections, in the similar way, D1 is equal to diameter at inlet section 1-1. Next, P2 is equal to pressure intensity. Calculate A1 is equal to area pi by 4 into D1 square. Similarly, we have to calculate D2 value, pressure intensity P2 value, velocity V2 value, and A2 cross-sectional area. These are corresponding to section 2-2. Now what we are doing, we are applying Bernoullis equation between these two sections. So P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Now section 2 is at the vena contracta. So now AO is the area of the orifice. A0 is the area of the orifice. Then this formula can be written as C into A0 A1 into square root of 2GH divided by A1 square minus A2 square. Whatever may be the formula we are using for venturimeter, same formula is applicable, but in this case convergent and divergent portions are not there. Because of this, what is happening? Losses will be more. So C is a constant. C is nothing but coefficient of discharge of orifice meter. Its value normally lies between 0.62 and 0.64. It is less than venturimeter, that is 0.98. It is less than 0.98. Next is petard tube. Petard tube, it is a device which is used to measure velocity directly in the laboratory. So here what is happening, whenever velocity of flow at a point is becoming 0, so its velocity head is converted into pressure head, or kinetic energy is converted into pressure energy. So based on this, our petard tube is working. So here you can see point 1 and point 2. These are two different points. Petard tube, it is a pipe bent at right angles. So we are considering point 1 and point 2 inside the pipe, right? So and the height of water below the petard tube, below the tube is equal to capital H. And here what is happening, since velocity is becoming 0, rise of pressure head is taking place. Rise of pressure head above the water level is equal to small h. So small h and capital H. So now what we are doing, we are considering two different points as shown earlier, and we are applying Bernoullis equation at two different points. P1 is equal to pressure intensity at point 1. V1 is equal to velocity of flow at point 1. So similarly P2 is equal to pressure intensity at point 2. V2 is equal to velocity of flow at point 2, which is equal to 0. Because velocity is becoming 0, then only kinetic energy is converted into pressure energy. H is equal to depth of the tube in the liquid. So now what I am doing, I am applying Bernoullis equation here. P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Z1 is equal to Z2 gets cancelled. So by substituting P1 by W value, V1 square by 2G, P2 by W value and V2 square by 2G, because V2 is equal to 0, we can easily calculate the velocity. So the velocity obtained from this formula is known as theoretical velocity. So actual velocity can be calculated by using some coefficient of velocity. So actual velocity V1 is equal to CV into square root of 2GH. So using that formula we can easily measure. And possible cases for setup of petard tube to determine velocity. Petard tube along with a vertical piezometer. So here you can see it is a vertical piezometer and it is a petard tube. So the difference in water levels can be measured. It is nothing but H. So V1 is equal to CV into square root of 2GH. You can measure velocity very easily. Similarly, it is second case. Petard tube connected with piezometer tube. So here it is a petard tube. This is a piezometer tube. Both are connected with a tube. And here we can see the water level difference is nothing but small h. So here by measuring the h value, you can easily calculate the velocity. Here you can see petard tube and vertical piezometer are connected with a U-tube differential manometer. Here it is a petard tube, it is a vertical piezometer tube. Both are connected with a U-tube differential manometer. Here you can see the difference between mercury levels. So similarly, petard static tube, which consists of two circular concentric, one inside and other with some annular space between as shown in figure. That diagram I will show you. Here two circular pipes are there. This is pitot tube. This pipe is inside the other pipe, and here also differential manometer is there. So here mercury levels, difference between mercury levels is equal to X. So by calculating X value, you can easily calculate H value, and finally we can calculate the value of actual velocity. This is about pitot tube, which is used to measure velocity directly in the fluid mechanics laboratory. Thank you one and all.